means that either everything is very exciting and understand something, or very much confusing. There is a mixture of the two. Okay. Anyway, more questions before I continue? As usual, you ask me questions and then I get some ideas about this stuff. So I also learn something new. So first, this 1/2 is not important. That's the first thing. I didn't mention that. I put 1/2 for some reason. You see now to simplify some derivations, but so if you want to minimize the function, you multiply by constant numbers. The reason that when you take the gradient is down. Then there was some confusion, and I think it's my mistake. Maybe some of these slides about the optimal separating canonical are a little bit redundant. So, if you are stuck, you can just look at this problem, and that's it. Okay, so let's do it. Let's look at this problem. Let's try to. So first of all, there was some confusion because here I have yi times this is the absolute value. As I said, it's the same because we have this constraint. But the reason it was confusing is before I defined the margin as the absolute value, then it was a bit confusing. So let's just start from this problem. You can also look at this. I could have written this also in a different way, but the same way, with the minimum inside. Maybe I should have written it like that. Or maybe I should not. I don't know. These are not my main doubts, but I will explain this stuff. Maybe it makes a difference. So the reason why I should have written the minimum inside is that before we define this quantity, right, with the absolute value, but now the absolute value is not important because it separates, as the margin of the hyperplane. So here you see clearly to try to maximize the margin. Does it make some sense what I'm saying? So by writing like this, the equation will be more directly linked to the colloquial, the statement of what this atmospheric hyperplane is. Right? So it's an hyperplane, so we define WB, which maximizes, separates the data with the maximum margin. The constraints say that it separates the data, and the quantity we maximize, right, which is the minimum for I, the distance, is the margin. So I hope it is clear. Is it? So that's okay. And, so yeah, so we want to understand now how we solve this problem, property of the solution, etc. And so now here we need to remember some theory which is not explained. So this either you know it from previous courses, previous years, or you accept it as black magic, or maybe you can try to study some books. So the point is that you can use the theory of Lagrange multipliers to solve the problem. Actually, we're not going to solve the problem explicitly, but to rewrite it in a different form and understand some property of the solution. Okay. So what we need to do is to form this function, which is called the Lagrangian, right? So which is a function which contains the objective function, the constraints that are there, and some additional parameters which are called the Lagrangian multipliers. And as you see, you have the objective function, then you have this sum of the Lagrange multipliers times the constraint. You have a minus here because the theory tells the Lagrange multiplier should be positive with constraints of this type, but the constraints are instead of this type, so you have to introduce this sign. Okay. The theory tells us that in order to solve the problem, I need to find a saddle point of this Lagrangian function. So at the moment, the problem that I had before is now this problem. It is more complicated because saddle points is more complicated. But in a moment, it will become simple. Okay. So I need to form this Lagrangian. I need to maximize over the Lagrange multipliers and minimize over W. Okay, so that's what the theory says. Okay. If I find the saddle point of this function, the W and the B will solve the initial problem. And there are some constraints here which are that the Lagrange multiplier are more or equal to 0. There are also some additional conditions we'll see later, which links the Lagrange multiplier to the constraint. So the constraints will be tight or loose, and depending on that, the Lagrange multiplier will be the opposite, okay? Loose or tight. So here, if we now we see that if we first minimize over W and B, we can get rid of these parameters. But however, there will be a formula which links this parameter to the Lagrange multiplier. Okay. And then we transform our problem in another problem, which is called the dual problem. It is similar to ridge regression, primary regulation, integration. And this dual problem will be an optimization problem in the Lagrange multipliers. So, and we get these equations. So if we minimize over B, B appears only here, and is multiplied by yi and alpha I. So when I minimize, I get minus the sum of these equal to 0. So I get this equation. If I minimize over W, then to take the gradient equal to 0, and here I get the gradient of this is just W, which is what I write here. And then we need to take the gradient of the second term, right, of this function. This is linear in B, so I can rewrite all this stuff as minus sum over I, alpha I, yi, xi transpose W, right? All this thing. So the gradient with respect to W is just the sum of this, minus the sum of this, which is what I've written here. So set it equal to 0, and then I conclude that W is a linear combination of the data with this coefficient. It's similar to the ridge regression, right? So we're also finding there that W is a linear combination of the data. So there are some similarities. And now I use this equation in the Lagrangian to simplify the formula for the Lagrangian. Okay. So what you do, so you need to substitute this equation here, and so we have, let's do it. Let's just do this. It's useful. So the first term is 1/2 W transpose W. Now the second term is minus, right? Now if you take all this stuff, right? I've already done it there, but let's do it here. So the sum over I, alpha I, yi, xi transpose W, right? Then there is a b, right, which is minus sum over I alpha I y I b. Then there is plus sum over alpha I. So just break all the terms. Now this term here, right, as w here, and then as this thing, which is just w because of the operation. So the first two terms altogether are minus 1/2 w transpose w. Can you read? Not very. I hope you can read from. Can you see what I'm writing? I cannot very well. So, it was y. Okay. So, the third term is 0, right, because of this constraint. The third term is 0, and the last is the sum of the alpha I. So, what has happened is that the Lagrangian, using this equation, has the simple form. It's minus 1/2 w transpose w plus sum of alpha I. And now w, you use this formula here, right? And you arrive to this following value in Lagrangian. It is minus 1/2, then it's sum over I and j. Then you have kind of alpha I, y I, alpha j, yj, and you have xi transpose xj, plus sum of alpha I. So just substitute the formula for that. So our problem then will be to maximize this quantity over alpha with the constraint that alpha more or equal to 0. So, so that's the problem where we have arrived using this Lagrange.
Are you saying that?
Yeah, from the beginning.
Just, I didn't understand the second part, the third term, don't go to 0.
This one. This one. Yeah. So, before I say that, we use some mathematical theory which tells us that if we have this optimization problem, the theory applies to more general problems. Thus, in this case, we want to minimize some functions into some linear constraints. Then I can form this Lagrangian, which involves the function I want to minimize, this, and then it is a sum of the Lagrange multiplier times the constraint. And here is Lagrange multiplier is kind of this minus of I, and then I just call it alpha I. Okay. So the second term is the one which comes as a constraint. So there is a well-defined procedure to build this function. The objective function minus the sum, the positive alpha I, multipliers times the constraint. And then there is a theorem which says that if I find a saddle point of this Lagrangian, right, so to minimize the W and B and maximize the alpha with a constraint alpha I 0, then the W and B we solve the initial property. And there will be some relationship which I will explain later between the alpha and the W and the B and the saddle point, which are called the Crouch-Kuhn-Tucker conditions. So this is the theory that we use. This last part for later. So if I can manage to find the saddle point, then I have a solution of my initial problem, so my optimal separated hyperplane. So my hope here is that this leads us to a simpler problem. But it's a hope, because at the moment it looks more complicated. However, in this case, it is easy to minimize over W and B in this function, right? Because there are no, I've removed my constraints. by formula function. And the objective function is quadratic in W and B, and B is linear, so when we take the gain with respect to B, the derivative, I get this constraint. When I take it with respect to W, I get this formula. And then I substitute these two equations in Lagrange. And so in this, so this one is not clear. So I wrote these steps, and so this is a quantity. This one is, as you see, is the sum of this, and this. So I break it into three terms: this, and this. So the term involving B will have B times so minus the sum over I alpha I yi, because yi multiplies also B, right? So we have this sum over I yi alpha I yi B. But so I can also put B here. Now the sum over alpha I yi is equal to 0 because of this. So it's 0. So because of that. So this is the writing of the problem where I was able to remove W and B, and it's for me. So, and one more problem. We are not done yet. So there is one more problem. Okay, so it's the pain is not. But this problem that we have found. First is a problem which involves a matrix which is m times m. So like with this dual representation for linear regression. It's a smaller dimensional problem if the sample size, if the number of training points is more than the dimension. And also, maybe you can appreciate this problem as simpler constraints. Although the objective function is a bit more complicated. So in the previous problem, the objective function was just W transpose W. But here the constraints are kind of simpler because, well, if you accept this one, the constraints are just alpha I more equal to 0. So, anyhow, if I can solve this problem, then the question is, how do I use the solution of this problem to find my homogeneous separator at a plane, which is all what I'm interested in. Right? So here you need to use these Kontaker or Cauchy-Kontaker conditions. It says the following. So first of all, if I solve this dual problem, the solution of the primal W, we had the equation just given by the linear combination of data points with the coefficients alpha I times yi. That was what was nice before to the right. But now there is something interesting that we will see in a moment, that many coefficients here are 0. Right? And those which are not 0, the associated point, data points, xi, is called a support vector. We will see why in a moment. So, and the other issue is how do we find the threshold B? So, so these issues are solved, need these Kontaker conditions. So what this condition says that the Lagrange at the optimum, at the saddle point, this equation, these nonlinear equations are true. So the Lagrange multiplier times the constraint. Right? So my constraints initially were of this type, right? More or equal than 1. Right? But I can rewrite it by putting everything on one side. Right? So here I take the 1 on the other side. So it's like minus 1. So the Kontaker conditions, I miss 1k here. I don't know where the history of these results. They are from the 50s. There are some nice books by Bertsekas from MIT, who I think wrote about 20 books in the you know, and is millionaire because of that, because he has his own publishing company. So he doesn't give it to Springer or to Wiley, but it charges the same amount of money. So anyhow, he has written many books, maybe 3 or 4 on this topic, and they are good. They are good books. They discuss, they prove these results. So I think there is also the crouch here. I think the reason they put it there because I don't know how to pronounce it. Just a little joke. So the constraint times the Lagrange multiplier is equal to 0 at the moment. So either the constraint is tight, so 0, or the Lagrange multiplier is 0. Right? If the constraint is not tight, it doesn't play a role in optimization. We just didn't know in advance, but could have removed the constraint, the same solution would have been found. Right? If the constraint is tight, it plays a role. So if I remove it, I'm going to find a different solution. Unless there are some atomic, I'm going to find a different solution. And now we will see that there is a corresponding geometric picture in the data points, the separating plane, etc., etc. So in a moment, let's go slowly. So we see that if alpha, the Lagrange multiplier, which is important because it appears in my expansion of the weight vector, right, as a linear combination of data points, Lagrange multiplier, which are firing, which are different from 0, which are more than 0, can only be those which corresponds to points which satisfy the constraint, which are tight. So here you have 3 points, like this, and this. And these are the points which satisfy the constraint. These points are equal to 1. They are at the distance 1 over the normal W. They are the closest point to the separating line in this case. And as you can see, well, unless I made a mistake, this is really optimal separating line, and it's tilted in a way that it stays as far as possible from the closest points. You can compare to this one, which is instead closer. Right? So with this point is very close. So what is more, what these mathematical steps tell us, and there is a clear geometric reason for that. They tell us that the optimal line is identified, is parameterized only by these, in this case, 3 points, which are called support vectors. Right? And the reason comes from these KKT conditions. The constraints, either the constraints are tight or the Lagrange multiplier constraints are tight. So, Lagrange multipliers. So, well, finally, you can find B by using one of the type constraints. Solve for B. Right? So, we take one of these constraints, which are equal to 0, and then derive B from that. So, yeah. Any questions? So, there are 2 difficulties so far. Yeah.
How do you get the B and then?
The B, I get it from I take one constraint which is type. Right? So I have yi times the linear function is equal to 1. Right? And I multiply times yi left and right. So this is equal to 1. So yi squared is equal to 1. Okay. 1 square or minus 1 square is equal to 1. And I put the yi here. Then I get b equal to yi minus w plus 1. Like that with some algebra. I use a tight constraint to derive b. Because w I found from this equation. Then it remains to be found b. And b I find from a tight constraint.
Okay, so y squared equal to 1.
Yes.
Is from the constraint before.
Why I square equal to 1 is because the labels are plus minus 1. Sorry, the yi are plus minus 1. Oh, this is important here. The yi are plus minus 1. They are talking about binary classification. We are talking of multiplication, not multiplication. So, yi squared. You see, mathematically it's important that the one class has minus 1 label, the other has plus label, because they work with 0, 1. Right? That's actually what binary means, 0, 1. So here it's important to have these two numbers because of the algebra. Right? So I write the constraints in this form. Right? So there are two difficulties here in digesting the stuff, which otherwise I think it's kind of intuitive geometric picture. The first one is to kind of absorb a little bit all these ideas of hyperplanes, separating, optimal separating, the parameterization, which led us to this optimization problem, the very first one that I wrote. So the first difficulty is to kind of be comfortable with the path which brought us to this problem. So kind of summarizing what we saw so far. And unfortunately, I overwrote the slides. So that we arrive at this problem. So in order to perceive the proposal, right, what this problem is doing, you need to remember the distance of a point from the line, hyperplane, and then this idea of separating, etc. The solution of this problem is the optimal separating hyperplane. The second step is to rewrite this problem in a simpler way, right? What we've done, and use Lagrange multiplier to gain further knowledge, properties of the solution. So what we have gained now is some simple. We have understood, we have arrived at some simple properties of the solution, right? For this Lagrange multiplier. So the solution depends only the weight vector. The weight vector is what is important. The threshold B can be found by solving this equation. The parameter of my optimal separated hyperplane involve only few points, which are called the support vectors. So the weight vector is a linear combination only of the support vectors, which in this two-dimensional example were 3. And this is not a constant that there are 3. Right? So unless you have some pathological situation, if you think about it, if you have some points here and some points here, you try to put a line in between. If you think about it, 3 points are enough. Right? So there are 2 points here which are closer, and there is 1 point here, or vice versa. Or they could also be 2. Right? If the points are kind of like this, they are positive, they are negative, it will be only 2, which will be the tip of these 2 sets. Right? So very few points are involved. Right, and what is more, right? So because of this, because we just need the separate vectors, so you can remove all these points which are not separate vectors, right, in the data, and if you solve the problem, finding the optimal separated vector plane for the points which remain, which are the support vectors, you will find the same solution, right? So here, You solve the problem, and you find out that the weight vector is near combination of this point with some coefficient. So let's say you find that, right? If you get rid of all these points, right, all these points, you just keep this tree, and you rerun the algorithm, it will be a smaller optimization problem, because there will be only 3 parameters to find. But you will find the same solution. Because clearly, these points they fix the line, so you cannot move it. If you move this line, you decrease the margin, because it's kind of in an optimal position. So what would be interesting here to do, when I don't have the software, is to do a simulation where, step by step, you build that. But we will see how to do that. Right? So this could be a very interesting exercise for you. Actually, this is not an exercise. It will be a project of maybe 15 years ago to solve this. So if you had done a good project 15 years ago, maybe now you will be famous, because a lot of papers have been written on this topic, and some of them are very much cited. How to find this guy? How to find this? That's a big question. So how to find efficiently? Here we just say what the properties are, but there is much more to say. Is how do I use this stuff? I need to find the parameters. But these properties that there are only the solution depends on the subvector, the vectors. It is used to find the solution. We'll see a little bit about that. Right. And then just to remember that we are doing classification. Once I found all the parameters, right? So the coefficients alpha and the vector b bar, right? So the vector w and the constant b bar. Then I classify by negative sign for my linear function. Right? That's how the classification. And so here I've written it again in this form, because then we will see that when we use kernels, here we put the kernel, etc., like for each regression. Okay. So so now, what we want to do? The next step is to relax the separability condition and discuss how. What do we do if the data are not separate? Can we still speak of an optimal, approximately separating line or something like that? Or how do I use kernels? And that's it. And a little bit about how do I solve the problem. So let's start with the non-separable case. So, if the data cannot be linearly separated, well, there is no hyperplane to separate the data, I can still modify my problem, my primary problem, right, with the hope of finding a meaningful solution. So the way I modify the problem, I use what at the moment is a heuristic, is to introduce some additional variables, which are also called slack variables. These are these xi. So for each point, I introduce one more variable, which is part of the optimization, the optimization. Right? This is called xi or xi. And so since the points will not be linearly separable, some of them will not satisfy the constraint without the original constraints. It will not be possible to find vector w and constant b such that these constraints are satisfied, because the points, the data is not linearly separable. So my hope is that by introducing these additional variables, now the modified constraints will be satisfied, which of course that surely is, but with a minimum perturbation. So in other words, my hope is that I need to switch on only few of these xi. the other will be 0. So many constraints will still be as before, with the separability constraints. Few of them, I hope, will be sufficient to, so there will be only a few points that you have to will violate the constraints. So my hope is that there is an underlying function, underlying hyperplane, which does not separate the data, but violates only few of these constraints. And the way I kind of search for this approximately separating hyperplane is here by putting the objective function, the sum of these slack variables. Take the sum of the xi I. Right? And so the xi I are more or equal to 0. And so here, and this C is a parameter, which is like the regularization parameter, as we will see, like in the case of rigid regression. So here, I hope that since I minimize this objective function, I will find only, I will try to make as small as possible this, actually the sum of the xi I, but indirectly I will try to make as few as possible xi I more than 0. That's the idea. It's an heuristic, so not very clear why it is doing exactly what I'm saying it's doing. So it's an heuristic, but I think there is an intuition behind it, an intuition that we want to violate latent constraints. You want to satisfy your constraints, so you need to introduce traditional parameters, but you want these traditional parameters to play a little role as possible. Because we like to separate the data, we don't separate them, but we want to don't deviate much from that. Right? If it is possible, because the data could be completely how do you say, mixed. Interspersed. Interleaved? No, interleaved. So in that case, we are. So for example, we could have a stock market. Give an example. And X could be a stock, an asset. The value of the asset during the past 10 days. And YI could be, does it go up or does it go down tomorrow? Big question. Now, if you look at this data, they are very much overlapping, the positive and the negative. So it's a very difficult problem, right? Because if you can build a classifier which has 47% error, but you're sure that error is 40%, 47%, you make lots of money, right? So that is a very difficult problem. And in that case, there is no hope that you can, well, there is no hope that you can have only few this xi I more than 0. That it will be a mess. Right? So here I'm thinking more of a situation in which the data are, they're approximately 0%. So the point is that we can still do the same mathematics as before, because we still have a quadratic problem. So we still have this quadratic objective, linear constraints. So we just have more constraints, twice as many as before, because there are m constraints of this type, and then there are m constraints, let's say, xi I 0. But we can use the same principle, same principles. This is not done here, right? But it is left as an exercise. But I will describe it briefly. You write this dual problem. So the dual problem is modified. It's exactly like before. There is only a novelty, which is important, which now you have this constraint. Alpha I is less or equal than C. C was this parameter which was balancing the norm of W with the sum of the xi I. And now this parameter C appears on the constraint. We have exactly the same problem, exactly the same dual problem as before, same objective function, same constraints, with one new constraint per point, which is alpha I now cannot be bigger than C. So you kind of limit the value of these parameters. And now if C is very large and data are separable, you find the same solution as before. That's kind of clear, right? Why is the case? But if data are separable, right, we know that if we solve this problem without the other constraints, we find the optimal separated hyperplane, and then we have some alpha I bar, the solution, and the largest of them will be equal to 200, let's say. And if I put here in this problem C more than 200, I will find the same solution. And because I have just that solution is contained in this constraint set. So the question is, what happens if data are not separable? Well, in that case, you need this parameter, and this parameter kind of traced off the error that you make on the data with the margin. And there is a picture here. So what you can see, well, first of all, you can go through the contractor conditions again, and they're a bit more complicated because they involve two constraints. So this is a bit more technical, and I would say it's more important to understand linear separable case. Okay? But please listen to this because it's very important if you want to use this stuff. But the message is that it's a bit more technical than before, understanding what the properties of the solution are, but it's very much similar. So we still need to use the Lagrange multiplier, the Tucker conditions. There are just more Lagrange multiplier and more Tucker conditions. The reason is that you form this Lagrangian, right? Now you have also some parameters which are called beta, which are associated with this constraint. Right? There are two types of constraints. Okay, so this is the first, and this is the second. So we need to build our Lagrangian by taking into account both constraints. And so this is the objective function, and then I do minus sum over I alpha I, and I put the first constraints. I don't write it. I need to write it. Everything on the left hand side, and then you have minus sum over I beta I ci. Then you put the derivative of W and B equal to 0. Do some algebra. Then you substitute it back in the Lagrangian, and then you find out that you have only an objective function of alpha and beta. Also, what you find out that beta disappears. So indeed, you only get an objective function of alpha only, as I've written here. What is beta? This is objective. So after you do this, you write this problem. So it's only alpha, which. Okay. Do you want to see these, or you think it's enough? It's enough. This is explained in the book. You want to see it more, a bit more into details. Up to you. We have time, but not too much, but we have time. Any preference? Skip.
No.
See it.
Do it, yeah.
So let's 5 more minutes, right? So the recipe is the same. We form the Lagrangian, which is written here. So and then I need to write explicit that here I have the constraint. Right? So I have the constraint, I put these guys on the left hand side, so I have yi W transpose xi plus b. And I have to take the derivative with respect to b equal to 0, and the derivative with respect to w equal to 0. The derivative with respect to w is the same as before here, because it appears exactly the same way as in the separable case. Remember, in the separable case, I don't have this term, and I don't have this guy. Otherwise, I don't have this. So let's just describe the novelty due to these three terms. All right. So the novelty is that, yeah, when I take the derivative with respect to psi, I also take the derivative with respect to psi, because it's one of the variables in the computation problem. Right? And this is what makes b disappear. So this is linear, so here I get the derivative with respect to psi I, I get c, and here I have psi I times alpha, minus alpha I, and here I get minus beta I, that it must be equal to 0. Then I get that beta I is equal to c minus alpha I. So beta disappears. Now if you use this equation and the two other equations that we have derived in the separable case, this is what you can do. Exercise and you get the book. If you use this equation and two other equations which are exactly the same, right? If I'm not mistaken, exactly the same as before, then the Lagrangian becomes the objective function of the dual problem exactly the same as before. Here you have the beta I are more or equal than 0 because they are Lagrangian multipliers, and then so this equation also tells you that c minus alpha I must be more or equal than 0, which is the same as alpha I must be equal than c. So that's why you get this constraint. So all these steps are based on the theory of Lagrange duality, which does we can transform our problem equivalent dual problem, and in the optimality condition involving the gradient, which allows to simplify this. In this case, we are lucky we can simplify the properties. We can take integrate equal to 0 over the prime parameters.
Now, so the psi I,
Yeah.
they're greater than 0 if the margin of xi is less than 1. Are they 0 when it's greater than 1? What's their range of psi I?
Yeah, the range of xi I can be anything more or equal to 0. But what will happen, and this is what is described here. In this slide, in the next one, now we will discuss them. A bit technical. These are the least pleasant, most painful slides of the note of the lecture. Not my fault. That's the stuff. So we need them to go through this Tucker condition and try to work out how the Lagrange multipliers are related to the constraints. So for example, if you do it here, you see that let's see. So you apply the rule, right? So you have the constraints, and then there are two constraints which are related. So the first is this one, right? So all these functions of the primal variables must be more or equal than 0, right? Everything that's been put on the left-hand side of the constraint must be more or equal than 0, times the Lagrange multiplier must be equal to 0. That's the first entire condition. The second says that the other constraint, which is just psi I, times the Lagrange multiplier, which was beta I, but as we saw, it is c minus alpha I. So by going through the steps which I made here, you understand why here I put c minus alpha I, actually it's beta I. That's the other Tucker condition. Right? So if we have solved for alpha, the dual problem. And if all the parameters here, all the variables, alpha, psi, beta, and w, are the saddle point of the Lagrangian, then this relationship, the linear relationship, must be true. That's what the theory says. And this, by analyzing these conditions with some patience and we understand something about the geometry of the line and the rho of the parameter of the xi line. So what we see, and this is what is explained in the next slide, but let me explain it by looking at this. So you have the kind of the bullet points and a little bit of the analysis in the next slide, but let me stay on this slide because so now what we need to do is to analyze these equations, different cases. Right? So the first case, which we do, let's assume that we have a point. So first, let's analyze these equations by thinking of where the points are, right? So, and right. So let's first do the equation, and then actually, let me first do it with a picture. Anyway, do you want to do a break now or in 10 minutes? No matter if you want to see this derivation now and then we start on the topic, or who is tired and wants a break now? You are really a break class.
Just keep going.
It's okay. So you don't want a break at all?
No, we do.
Okay. But tomorrow, as a matter of fact, I think most of you are in my class tomorrow. I have a little constraint, and I would like to make only one break at most. If possible, no breaks. Because I was told that in the old days in Russia was a very good school of science, and they were teaching for 5 hours. People were very happy. After they were having tea with marmalade. So anyway, tomorrow I have a little request for you to make less breaks. If possible, no breaks, but if you understand, you're so good.
5 hours in Russia, so they took vodka with them to the lecture room.
This, I don't have the data, but that's possible. I've been in conferences with machine learning, in particular of statistics, and there is an area which is called mathematical statistics. It's quite hard, theoretical, and there are many Russians, because Russians are very good at mathematics. And so there is always a day in which they bring the guitar, and they play until 3 o'clock in the night, and they drink somehow. So it's, they gather together. It's very nice. But what is fun, and the next day they give the lecture and solve problems. So anyhow, I have a deeper experience with that. So anyhow, so we can speak for 3 hours. It's just a matter of putting your mind in that thought. I'm joking. We can break anytime. So, 10 more minutes. So some of the stuff is a bit heavy. But, so the end result is what is in these pictures. So for example, let's look at this. So now there are two kinds of points, right? There are support vectors of first kind and of second kind of. So the one of first kind, so the support vectors are those which have the parameter alpha more or equal than more than 0, right? So they are those which play a role in the solution. Right? The solution, vector W is a linear combination, right, of the points, coefficients alpha I times yi, which is something important I haven't said. I haven't been about this. Alpha I times yi, in fact. So those which are non-zero are the support vectors. But now there are two possibilities, right? So the alpha I can be between 0 and c, but not equal to 0, not equal to C, or they can be equal to this parameter C, which so far I have kept aside. I haven't mentioned it much, right? So this is it's kind of the regularization parameter, right? Which says how important it is my new objective function there. Right? So what was that? Right? So this is how I modified my proposal for linear separated hyperplane. That doesn't exist, so I modified the problem by adding this term in objective, these like variables here. Right? And I found out that the solution of this problem, the vector W is linear combination of the data points, much like before, same formula. The vector B would be, the parameter B would be found by some algebra. In fact, to understand all this stuff, we could have assumed B equal to 0 a priori. We would have, the equation would have been a little bit simpler. Don't pay too much attention in B. You need it because then you can speak of the optimal distance of the point. So we have found out that solving this problem is equivalent to solving for this Lagrange stuff, this problem, right? And then there are these Kuntake conditions which link the solution of the primal to the solution of the dual. They together form the saddle point of the Lagrangian, and they need to satisfy these optimality need to satisfy these conditions, these Kuntake conditions. If we analyze this condition, we understand something about the geometric position of the points. Right? So let's do that now. Let us first consider the case in which, that's why I was putting this thing. So let's look at this. So the end result is the following. There are three kind of points. Those which don't play any role, they are not. And these are the points which are correctly classified and further away from the line than 1 over the norm of W. Right? So there are all the points which are. This is a terrible picture because you don't see these gray things. You should see it in the note. These are in gray. Fortunately, this is not very good resolution. Maybe also. So among the support vectors, there are two kinds. There are those which are exactly at distance 1 over W, 1 over the norm of W. These are in black. And these are like the previous one in the separate one. And then there are this one in gray. And this one in gray, they are at these are in gray are those which have the psi I switched on. The corresponding psi I will be more than 0. And these, so when I look at the constraints, right? In the original separable case, this was my, I want to find a line satisfy these constraints. Right? Now, these points in gray do not satisfy these constraints, so it is less than 1. And among these points, so this will be the point, as you see from these Kuntake conditions, which have alpha I, the optimum equal to C. Among these points, there are two further kinds, if you want to be really pedantic. There are those which are still correctly classified, because even though they don't satisfy this constraint, the constraint is more than 0, so they are correctly classified. And there are those points which are misclassified. So this last set is the set of errors which my linear classifier makes. So let me do the picture. Just kind of inverse engineering. So first I write down the solution for some points, but this does not correspond to the reality. Because I don't know what the solution is. So I have a line, right? And then I have these points which are at the distance 1 over the norm of W. So now it is important in this case, these points don't identify anymore the solution. The solution is identified by all the supervectors. Right? So this is something to understand if you go through the math. So when I have like these are like triangles and circles. One here and one here. So this satisfies the constraints with an equality. These are the points in both. And then I have some points. So let's say this is a triangle class, and this is a circle class. Then I have some triangles which are on this side, so they are on their own side, right? As determined by this dashed line, right? Which is not the separating hyperplane, right? But it's parallel to the separating hyperplane, and it goes through this guy. So all the triangles which are here will be supervectors, and we have a parameter alpha equal to c. This is the end result we're going to now see. Similarly, all the circles which are on this side will be supervectors, and we have alpha equal to c. Alpha I equal to c. So the typical situation could be something like that. One triangle here, here, and one circle here, and one here. Right. The circle could be all the way much far away on the wrong side of the line. And this will cause problems, right? Because outlier, formally speaking. So the solution will be influenced by this point being so far away. So there are.
So where alpha I equals c is in these areas.
Well, yeah, well, so if these are triangles and these are circles, yeah, they cannot be separated exactly by a line, but pretty much. So most triangles are here, most circles are here. I haven't put them there. If I run this graph with a certain parameter c, which later I'll tell you what this does, but a certain parameter c, I will find this line, and then I will have some, just a few triangles and circles which satisfy the constraint of inequality, in which psi I equal to 0. It will be this guy and this guy. And then I will have a bunch of triangles which are on this side of this dashed line, and circles which are on this side of this dashed line. So I have 3 lines. Right? I have the separating line, and then I have the parallel one going from this point, the parallel one going from this point. I could have more points here, right? On these lines, right? Nobody, I could have one more here. So in these things, you see it by looking at the tracker conditions. So let's do it now in the next few minutes, then we stop. 5 minutes maximum we stop. I hope. So, it's easy, right? Because if psi I is more than 0, it means that the constraint is less or equal to 1, right? The old separability constraints are less than 1, right? If psi I is more than 0. Then this condition tells me that c minus alpha I must be equal to 0, so alpha I must be equal to c. Right? All these points, I get them. Alpha I equal to c. So they become big bulk, like you sum them up, right? Because the coefficient is always c. Well, it's c or minus c because you have the alpha, you have 1i, so it's kind of the difference of 2 clusters. You can think about other interpretation of this stuff. But anyway, those are fixed. But it could be the case that what happens if then, all right, the other case is as before, right? Because I put psi I is equal to 0, right? And then I go back to this constraint, there is no psi I, and it is like in the previous case. And I see that if the constraint is not tight, so it's more or equal more than 1, more than 1 minus psi I, but psi I is just more than 1, then alpha I must be equal to 0, so I don't sample vector. Otherwise, if it is equal to 1, if I have these points which have this guy equal to 1, then these are candidate support vectors. So alpha I could be, typically is more than 0. Right? Logic tells us that, so there are two ways to this. If and only if. So if you look at, if you read the book, or I think this is in the book, or if you read through the slides, you will see that so one thing is to say that if psi I is more than 0, then alpha I is equal to C. That is true. Another thing is to say that if alpha I is equal to C, then psi I is more than 0. That's not true in general. Typically it is, but there are some pathological cases. So there are some details here that I hide. Okay, so and these are understood by looking at algebraically through these equations. But geometrically, the interpretation I think gives you many more insights. And the interpretation is that, and the result is that unfortunately things are a bit more complicated than that. So you lose a little bit of your initial part. So I think the separable case is much simpler. But you can still speak of separate vectors, and there are these two guides, etc. And if the data are just approximately separable, it is still true that most of the points are non-separable vectors, so most of the points are removed, and you still find the same solution. Right? And just to conclude before the break, what happens then is what happens if you move this parameter C. Well, what happens is that if you increase C in your objective function, right, when you have objective function, you will have this that you want to minimize, the normal W squared, which is like maximizing the margin in this, and then you have the error, so the sum of the slug vectors. So if C increases, you try to make this sum as small as possible, because it's the dominant term in the objective function. Right? So if C increases and the data can be separated by line, you will find that optimal separated line plane eventually. If they cannot be separated, you don't know exactly what will happen, but as C increases, what will happen is that typically you will have less support vectors, right? In the gray, less gray support vectors, and the margin, which is this gap, right? This is twice the margin. Right? So this thing is 2 over the normal W, right? Because the distance from the bold guys to the line is 1 over the normal W, so this gap twice that. Now this gap will become small. Your goal is to minimize the sum of the psi I. C is big, you concentrate on that term. The first term, which is the normal W squared, W times W, you don't pay much attention to it, so it will grow, right? It will grow, and therefore the margin, which is 1 over that, 1 over the square root of that, will decrease. So as you see here, the margin, which is this gap, right? Twice this gap, half this gap, becomes smaller and smaller, and C increases. Whereas, and here it's not clear, I hope in the slides it's clear, the sum of xii decreases as C increases. And also typically the number of these points decreases. although that doesn't need to be the case. Mathematically doesn't need to be the case, but also the number of support vectors will decrease as C increases. So we can stop here for 10 minutes.